Okay, so from last time we talked about the shearing forces in the welding material. So let me remind you what happened last time. If we have a structure being welded on another structure, and this one of the particular structure is being applied with a force, then the force could be providing some payload onto the welding material. So in this particular case, when we have a structure being welded on this, looking like a wall, and if you have a force on the side, it's gonna having a normal shearing stress going downward. So it's like this external force is pulling this structure down. So there is a normal shearing stress downward. And also, because of how this layout of welding material is being arranged in a certain shape, so there is gonna be a rotational center. So when you apply external force, that's gonna generate moment. You can imagine the whole structure is gonna rotate about this rotational center. So if you try to compute this kind of rotational load, it's gonna having a rotational shear. Okay, so this torsional shear is going to be perpendicular to this radius from the rotational center to the investigated point. So from this viewpoint, you realize everywhere inside the welding material is going to have the exactly same shearing stress coming down, but there's gonna be a perpendicular shear pointing toward different directions everywhere. So if you try to make a drawing of the welding material, let's say you have welding material arranged in this way, and here is the structure you have, and this is like a larger structure. So these are the welding materials. Now, due to this external force, so everywhere inside the welding material, there are some normal shearing stress downward. And if you have a rotational center right here, and you try to investigate at those points, there's gonna be rotational shear as well. So there's going to be a rotational shear like these, and with different amplitude, different amount. So in this particular chapter, what we care about is which point is carrying the most shearing stress. And that is going to be the critical point. And if our welding material is going to fail, that particular point is going to fail first. So if you take a look at the equations for shears, this is the equation for normal shearing stress, and this is the equation for this rotational shearing stress. Following this, you can say it's a polar coordinate. Okay, so because it's following this polar coordinate, the area moment of inertia is actually the polar moment of inertia. Polar area moment of inertia, J. So usually when you take a look at the textbook, and when you study for, if this is an x coordinate and y coordinate, usually the book tells you I-x-x, I-y-y, and also sometimes people use IZZ, or sometimes people just call J. and j can be computed by ixx plus iyy. Okay, so what is ixx being used? Is going to be a kind of I usually treat area moment of inertia as a kind of ability to fight against rotational moment. So when we have bending, and if you have larger I on that particular rotational orientation, this material, this cross-section area can fight against this moment better. Okay, so Ixx represent bending and rotation about the x-axis. Iyy is used for bending, fighting against the rotation about the y-axis. But J is going to be about the z-axis. So if you have a torsional shear that is rotating about on this particular plane, then when you are studying for the area moment of inertia, you are actually talking about the area moment of inertia that is rotating about the z-axis. Okay, so here we are doing that. So J is talking about, it's like if you have a larger J, the material can carry heavier loads. That's going to generate this kind of rotational shear. Okay. So last time we already talked about how we are going to compute J, but we have to stop because of at the end of the next lecture. Let me remind you that you can compute for J of the left geometry and the top geometry right at the center of the shape. So JG represents the polar area moment of inertia right at its geometrical center. So you have JG1 and JG2, but you are now combining two shapes together. You are treating them as one piece. So you have to find their common center of geometry. So first, you need to figure out where is the location for the overall G. Last time we talked about how you can treat it like a balance for moment. And it's like you have a support, you are finding a proper position so that these two G's have like weights coming down. So you need to find the proper position so that they are balanced. So by balance of moment, you found X bar, where is the X component of this G position. And you do the same thing along the Y direction, then you find Y bar right here. Okay. So once you have found that, next will be computing for the polar area moment of inertia on the G point, not G1 and G2. So for the left shape, now you are going to use the axis parallel theorem. So here's a reminder of the theorem. For any particular shape, if you check a reference, it tells you how you can compute the moment of inertia right on the center. But if you are studying with a different center, then you need to figure out the offset. The axis needs to offset toward a new position. So the offset is like a radius r. When you do that, now you are studying the same shape, but the rotational center now is at a different position. So what would be the area moment of inertia of this particular shape about a new center? Then this J0 or JO can be computed by JG plus the size of the area times the radius squared. Okay, so J0 equals to JG plus AR squared. That's why right here it's going to compute this R1 and R2 by geometry. Then the overall J can be computed by this particular JG1 plus the area of A1 and radius 1 squared. But that's only the J for this left-hand side geometry on the G point. You also need to plus the polar area moment of inertia of the top geometry investigated on the G point. That's why you have the second part, JG2 plus area 2 times the radius 2 squared. Okay? So that's how you compute J. Now, once you have this J, actually the whole problem, the most troublesome part is to compute J. Once you have that, then you can investigate any particular point. You will have a normal shearing stress, and you will have a rotational shear. So if you, and the way to compute it is by the equations over there, these two. And actually, you may need to do some integral if you want to balance the whole thing. So what's happening is if you are investigating a small portion right here, and if this is having a small distance, let's say dx, okay? So you can compute the normal shearing stress coming down and also the rotational shearing stress that is normal to this radius, and you can get the shear for the distributed shear on this small area only. And overall, to sum up, you can figure out what would be the moment, total moment everywhere. And it will be balanced out by the overall moment created by the external force. And if you have a distance right here, if this is d, so the total moment, of course, equals to F times d, right? So there will be reaction forces everywhere, and every reaction forces will be slightly different because of how this geometry look like, and the delta of those moment everywhere needs to sum up and will be balanced out by the total moment. So that's how you could be studying for the particular shear everywhere. Okay, so let's take a look at some of the examples later on. Let's Move on to example. Total moment. I think you don't need to the moment FL. In this particular case, F is right there, and 25, 100 times. Okay, so let's take a look at this example. So here's another quite practical example where you have some beam structures, and you are going to combine multiple mechanical components together by welding. So this is if you say this is the front view, then this is the right view. So over here you can see how there is a structure that's going to be utilized for some kind of axis, and it's going to be welded on this particular, you can say is like half of the I-beam, okay? And there are symbols indicating where are the positions for welding. So this corner and this corner. And also from the right view, you can see it's also indicating where you have welding materials. So from this view, you already see this horizontal edge has a line of the welding material, and these two vertical edges are also having welding materials. So the example already shows us how the welding materials look like. And the problem implies that there's gonna be forces applied to the axis, to the rod on the top. And because there are two sides, so one side of the welding material is going to share half of the external load. So this problem only takes care of half of the external load and only focus on one side of the welding material. Now, for this particular case, what you need to do is to figure out the geometrical information, and here is where the center of this C-shaped welding material is going to be located. So let's see if the problem computes for you. You can follow the exact same way that was introduced last time in order to find out the position of O. So that gives you key information about where the rotation center is. And the total moment is going to be generated by this 25 kN times this 110.4 maybe millimeter. Okay? And so there will be reactive shearing and also reactive moment to balance out the external force. Okay, so this reactive shearing balance out this external force going right, and this reactive moment balance out the external moment caused by this external force going right. And this reactive shearing, normal shear, and the rotational shear due to the moment will be distributed into all the welding materials. So right here, first of all, it computed the total area. And what is 0.707? Basically, is from the last time we talked about how the necking area, if you have welding material in a triangle, and here is your width of the welding material, then this throat dimension will be smaller than the width, and it's basically 0.707 times of your width. So that's why there is a 0.707 times of that area. So a shorter throat is going to lead to greater shear, greater stress, because smaller area here, greater shear. That makes sense, because if you only study for the original geometry on the edge, that's not the most critical area. The most critical area is on the throat, where you have the smallest effective area for stress. Now these are just computing the length. So 2 times 56, so both sides, and then 190 for the top. Okay, so that's the total area of this C shape. And the normal stress basically is going to be the shearing force, the force over area. That's how you can compute it for shearing stress. So basically there will be shearing stress going horizontally everywhere inside this C shape. Next, what's important next is you need to compute for the center. 10. It's actually right here. If this is the y-axis, then this is x. So the coordinate was given as the vertical one was given as x, and the horizontal one was given as y. So over here there is a short distance. If you treat here as the origin, then the problem is trying to compute where it is x bar. So right here, you have to bend your head by 90 degrees and treat whatever on the left. So it's like you are bending your head. Now you are seeing the C shape in this orientation, and it's like you have a you need to figure out what is this x bar, right? So you will have one geometry here. You can treat this horizontal part as some material with some weight. So there's some weight here. You can say this is like a W1, and this is like a W2. Also W1, they are the same size. And it's like here you have a W2. So they need to balance out. And you have tried to figure out where you put your support so that this whole thing balances out. So in this case, here is 56. Okay, I'm trying to figure out how yeah, I think it's using this as a center. Then so supposedly if if this is going to balance out, then you should have W2 times X bar equals to 2 times W1 times this particular distance. So that distance would be half of the 56 or 28 minus X bar, supposed to be. So 28 minus X bar. So, and the W is going to be proportional to the length. So you can use the total length right here to represent W1. So that would be 56. So 2 times 56. Here should be 28 minus X bar. And here is 190. 190 X bar. So 190 plus 2 times 56 X bar equals to, I take it to the left, so here should be 2 times 56, 2 times 28. Am I right? Yeah. So that's why X bar at the end equals to 56 times 56 over 190 plus 2 times 56, right? The same equation. But it's for the equation right there, it's a quick jump. But right here, I think it's I take it slow. Basically, you are trying to figure out where's the location right here, and you are treating those materials are like weights. And the weight of each particular component is proportional to the length. Okay? That's why your W2 can be replaced by the length of this part. And your W1 can be replaced by the length of the horizontal part, right there. That's how you compute X bar. So once you have X bar, the rest are simple. You are just going to compute the radius. And why does this textbook, why does this example show you the radius for A, B, C, D corner points? Because that's where you have the most probable positions that has the greatest shear. So, and because there's normal shear and this rotational shear, and they will be having different angles. So in order to try to figure out what's the overall maximum shearing, combining the normal one and the rotational one, you really need to compute all 4 situations. So right here, the radius from the center to A and B can be computed by some geometry right there. And the radius of C and D from O can be computed. So the radius were computed. Then the rest are just trying to figure out. Also, you need to compute for J. So here it's already done with JG1 and JG2. So if this JG1, JG2 were being computed, and it will be offset to point O following this equation. So JO is computed with the JGs as the geometrical center of each rectangular part. So these are the JGs, and also the I think it combined multiple equations, because this is the x bar. So area times x bar. So multiple equations were combined. So basically, I plan not to spend too much time on those. So anyway, JGs were computed, areas of everywhere were computed, radius were computed, so this is how they were combined. So at the end, this J is going to be the overall polar moment of inertia for the entire C geometry, C shape. And the total moment is computed by the external force here multiplying the distance 110.4. So that would be this one, the total moment. So the shear at the corners will be computed by moment times the radius, which was computed at different corners, and divided by the common J. The J are the same. So once it's done, you can make drawings like this. So the overall effect is like this. Due to this horizontal external force, there would be a reactive shearing stress fighting against the normal force, so going left. So we are now talking about shears due to reactive forces. So at all four corners, there are exactly same horizontal shearing stresses going left. But at ABCD corners, this external force is gonna having this clockwise moment. So for the shearing stress caused by the reactive moment, that is going to rotate on the opposite direction, which is counterclockwise. So right here, if you take a look at point A, the reactive rotational shear is going counterclockwise. Here, counterclockwise, and also this one, counterclockwise. So overall, at four different corners, their normal shear is the same, which is going left horizontally, but their rotational shear is pointing at different directions. What you need to do next is to compute the overall shear at all four positions, and then you will figure out which point is having the largest overall shear. So the book already did the math for us. At the end, points C and D are having greater shearing stress. So in this particular case, without true calculation, before you truly learn about this chapter, you probably have no idea which point inside this welding material is the weakest. So in this particular case, you have some like a horizontal bar, and you have a force applied toward onto the bar, and you have this C-shaped welding here, and in the end, the weakest point will be C and D because they are carrying the most shearing stress. So if it's going to break, it breaks from C and D. Okay, so that's why this chapter I feel like is quite important, because without this kind of knowledge and truly diving into the equations to figure out the shearing stresses everywhere, it's really difficult for human guessing to figure out what is the largest shearing stress point. Okay. So the rest of the chapter basically shows you examples of welding materials in different shapes. So, and there are some known equations, because you know you usually weld the mechanical parts in some common shapes. So this chapter sometimes will also provide some known equation for you. So you don't need to do all the math again and again. Okay? So like this particular problem here is telling you, okay, if you have fillet welding, and if you are having geometries like that, then the horizontal length is B, vertical length is D, so your center for this area moment of inertia would be located at X bar and Y bar. X bar, due to symmetry, X bar can be easily determined by half of the B, but Y bar needs some certain calculation by balance of moment. So this table tells you that some numbers, okay? And do we use I? Well, basically that's J, but in different symbols. I think that's the second moment of inertia. Yeah, that should be. I think that's yes. That's. Is it J? 12. No, it's a different. It's for the bending. It's for bending. So it's the area moment of inertia for bending. So I only. But does it tell? Is provide you the? It doesn't provide you J. Okay. So at least there are some tables that already did the math for you. Right here, in the table, IU part is right here. Okay, and at the end, I equals to the effective area times IU. So the table already did some calculation for you, but you need to update the I by the 0.7 times of the IU. Okay. So anyway, I would like to only cover the welding chapter up to here. So like I mentioned last time, we are reaching to the end of this course, but I think I mentioned about mechanical design. So when you are truly designed for something, you may have issues of multiple safety factors. So I would like to mention a little bit. So let me move up and just use the board to tell you what I would like to say. When you are truly designing for something. So in most of our chapters, we usually have design variables with usually one unknowns. Okay, so, and we usually apply for safety factor on that particular unknown. So why is that? Because we only can deal with simpler issues. So take one particular scenario as an example. You may have, for whatever design, you usually focus on the stress for your design. And you usually have a limit, right? So usually you would like to have a design equation like this. But that allows you to move your design toward the limit and even right on top of the limit. And for this entire course, we are trying to tell you that we don't want to be too close to the limit. So why is that? Because whenever you request for this particular design, in reality, it doesn't always deliver the same component. So the stress could have uncertainty, some distribution. Okay? And even your limit may have uncertainty. Why is that? Take one simple equation as an example, and C over I must be smaller than yielding strength. Okay? Due to geometry, this is related to geometry, right? I is related to geometry. Also, C is related to geometry. M is related to the amount of your force. And yielding strength is related to material property. Okay? So how are you so sure when you build something the dimension is exactly in the exact size? Maybe not. So your geometry may have uncertainty, right? And when you apply a force, how are you so sure your force will be the exact amount that you are investigating? Maybe not. So also, force could be uncertain. And also material property, when you check the textbook or check Google information or even ask for the manufacturer, it tells you, okay, the yielding strength of this particular material is certain level. How are you so sure? So this is also uncertain. Okay? So in this particular problem, actually, everything is uncertain. That's why there could be some chances. Maybe you ask for this particular stress with this design, but there is a chance the real value, the real stress is right here. Maybe in one probability. And one of the probabilities is that your design is located right here. And if you're unlucky, the material has a chance that the material strength is on the left-hand side of your design, right here. So in this particular chance, your design is having a stress that is larger than the limit. So when you are, but since they are at the tail of the distribution, so the chances are lower. So that would be fine. However, if you move your design, if you allow your design stress to be closer to your limits, So if this is your design, and this is your limit, then this is the mean value, and this is like a distribution of your design, and the distribution of the limited stress. Then you would have a greater chance where your stress is greater than your limit. So that's why you don't want your design stress to be too close to the limit. And one trick is to apply safety factor here. So you provide some kind of new limit. So this new limit equals to your original limit divided by safety factor. Sometimes people say NFS, so factor of safety. So it's gonna be some value smaller. So your design limit now only can be up to a certain level. Okay? So how is this how is this determined? So usually it's like this. In fact, if you have your design stress, and here's your limit, and here's your distribution, and let's say right here, right now, your design is on the limit, which is equals to limit divided by the safety factor. Then this area is your failure rate. So usually safety factor is designed so that your failure rate is acceptable. Okay, so in the future, how do you evaluate your safety factor? Basically, you determine how much failure rate you can allow. If you are asking for even lower failure rate, then your design needs to be moving away against your limit. So your design space becomes smaller. So this is only for 1D problem. This is one dimension. Because you are only focusing on one particular stress. But in reality, it's not that easy. So here I would like to share with you that you may have multi-dimensional problems where you could be having, let's say this is stress 1 and stress 2, and you could have stress 1 of your design and stress 2 of your design. So now you are having a design point which is in a two-dimensional problem. It's like you have two design variables, and you need to pay attention to stresses at two different positions, but somehow they are kind of related. Okay? So, in the traditional way, for stress 1, you have a limit. So this will be stress 1 limit, right? And stress 2, you have a limit. So it's like you would like to generate some kind of safety gap away from the limits. And the safety gap usually is designed by the ith design must be smaller than the ith limit divided by the ith safety factor. You can have different level of safety for different dimensions. So usually you treat each dimension individually. But here I'm just trying to let you know, in the future, when you are dealing with this, you actually have a more complex issue. Because for the first dimension, if this is a normal distribution along this direction, and if along the second coordinate, it's also normal distribution. In that case, actually you are, when you view this from the top, it looks like a contour. If you can observe like this. So in that case, now your normal distribution is like a dome shape. Okay, so what's gonna happen is you may have a coupled effect between two factors. So sometimes you have coupled like limit conditions. Sometimes like that. So limit. So what does that mean? It's like you have a new limit that is related to the stress of 1 and stress of 2. So one particular case probably would be the sum of stresses must be smaller than a total limit. So if this is the case, then you may have an equation like stress 1 plus stress 2 has to be, if I call this stress bar. So you may have a simple equation like this, but if you make a drawing of this in this particular figure, then it's a 45-degree linear line, and now it's very complex. So the failure region is actually on this area. So this is where you compute the failure rate when you have coupled conditions. Okay? So I just want you to know, now we have learned individual components, but when you put things together, there will be design problems in each component, and they may be coupled. Meaning, whatever you are investigating in one component may be related to the other component. When you are trying to change the dimension of one axis, one cylindrical axis, cylindrical rod, and if you have a bearing on top, when you change the dimension, the bearing changes as well. Right? So they are coupled. So in your project, I think you can also think about what are the choices. Not just focus on one component or one dimension. And you will realize, oh, actually, your decision your decisions everywhere are very related. And you can try to list out all of the design equations for each component. And please make sure if you can separate them. If you can design each component separately, meaning whatever you do on this particular dimension has no effect on the other dimension, then I think you're fine. Then you are dealing with some kind of so-called a separable problem. So whatever you are considering, they can be individually investigated. They are not coupled. Then you're fine. You can just treat them like how you usually do in each mechanical components. But if there is a certain design request that has couple effects, like a very simple equation that I show you right here, then these two design equations are related. If you enlarge the stress right here, maybe the stress on the other side needs to be reduced, because there could be some coupling effect like this. Then it's harder to figure out the safety factor. Okay, it's harder. Okay, so there could be issues like this when you have, in fact, this one, because it's linear, is not that critical, because now you are dealing with design equations with some safety gap, but now along this coordinate, this perpendicular direction. And you still can have some safety factor right here that can be determined by certain safety level along this coordinate. But so when it's a linear problem, it's simpler. Okay? However, when it's nonlinear, then it's very it's not easy. Okay? So I would like to, at the end of this course, I would like to just share more with you about what's going to happen in reality, and you have one more week to work on the project. I plan not to introduce more, so this will be the end of lecturing. Do you need some time for project discussion? Like tomorrow we have 1 more hour, do you need discussion? If not, we don't have to. So if we don't have this, if we don't have project discussion, then I will see you next week. So in your final presentation, for your final project, basically, I'm looking for a final presentation with a PowerPoint. So all the team members should come up and talk about what has been done from your group. And please pay more attention on some kind of force analysis, stress analysis, considerations of the either failure or fatigue, and talking about why you do this decision so that you have certain level of safety. And of course, since you are just proposing to certain design for certain ideas, there will be numbers that cannot be verified. So you can make your own guesses or assumptions, that's fine. But I hope in your final presentation and final analysis, the whole process will be a complete process. And if you can pay attention to multiple mechanical components, that would be great. Let's say you are reducing the weight of a metal plate. Once you do that, does that has a like an effect to other related components? So if you can pay attention to multiple components at the same time, I think that would be great. But if you really just pay a lot of attention on one particular component, that's fine. Then you are just trying to study the problem separately. Okay? And I hope maybe some group can talk about designs with multiple components. So once you complete your presentation, Dr. Patel and I will be giving you, we will have some QA session, so we will ask you some questions, and once it's finished, that will be the end of the course, but you still need to submit a final report. So the report is going to be a Word document style. So do we provide them some template for the report? Maybe you can discuss with Dr. Patel. So that's provide. If you have your own format, that's fine. So usually it's a document, like a Word document, and you can have your title and authors, like writing a paper. And then you can have abstract. Just briefly talk about what will be seen in this report. And you can have basic introduction. For example, you are studying some mechanical design in a mobile robot where the some part of the components is too heavy. So right now I'm trying to reduce the payload to the motor by reducing the weight. So once you introduce it, you can talk about more details in your own style, and you can have some analysis and talk about results and discussions. So I will encourage you to have comparisons. Because how do you show your result is better than the original design? Is by comparison, right? You can mention how much improvement you have made, and if you have studied some of the references, please list out all the references, right? So this is a good opportunity for you to practice how to write a report. And I know nowadays writing a report is very easy because AI is a good helper. Try not to rely too much on AI, okay? For myself, I usually use AI to proofread. So at least I will provide something, okay, proofread my the paragraphs I have written. I think that would be a better practice. Otherwise, you are just getting something quick from AI and you learn nothing. It's like taking drugs. AI is a drug. If you take too much of the AI drug, you are addicted. You cannot get rid of it. So you lose the ability to think about something by your own brain. You need an AI brain to help you. So try to use it to practice. You guys are looking for graduate study in the future. AI technology will be more advanced when you start your master degree. If you get addicted right now, then you lose some kind of training. Okay, anyway, I'm looking for PowerPoint next week, and I can give you one more week for your Word document. So if the project Word document is not finished by next week, that's fine. I will give you one more week. And if you have any, like a CAD file or ANSYS files, or any other files. So please also include that in your final submission. So TA will, at the end, just send to the TA. Yeah. Only 3 groups, so it's very simple. I don't need to like having a complex submission platform. Just combine them, send to Google or email, that's fine. Okay, so before I let you go, do we need discussions tomorrow? No? Are you guys okay with the project? Okay, so I'm not sure if I'm using the best way to teach, because I feel like the second half I tried to quickly introduce the components. This course was originally designed for 2 semesters. So each chapter requires 2 or 3 weeks of lecturing so that we can look deeply into the equations, solve for problems, lots of exams and homework assignments. But in our school, we reduced mechanical design into 1 course. So it's almost impossible for me to cover everything and ask you to do homework for every chapter and exams for every chapter. It's very, very challenging. That's why this semester I'm using this way. I still try to cover the components, but I only touch the surface. I didn't even jump into a very complex problem and ask you guys to solve it. So I hope you still can learn something. Yeah, I know for myself, if I'm the student, I may just lose attention, but I hope whenever I talk about concept, some part of your brain kept a memory of it. So in the future, when you need it, you know where to find the references. I hope the lecture is useful for you. Okay, so that's it for today, and I think we need to do attendance check. So once you are done, you can go. So I think we can skip tomorrow's course. Are you guys okay? Skipping tomorrow? Okay, great. Thank you. Since we are skipping for tomorrow, so the grading distribution will be, the score distribution may be slightly changed, but it won't affect too much. Okay. See you next week.